Okay, hello everyone. How did your homework go? Do you have any questions about the practice problems, basically? Anyone? Can you please go over 5D? I definitely will. Anything else? Okay, so 5D. So let me remind you the addition principle that I broke in two cases. No. So the addition principle told us the following. Suppose A and B are two sets. Finite. It means there are finitely many elements. Okay. Now, if the intersection of the two sets is empty, it means there is nothing in common between them, then the number of elements in the union is the number of elements in A plus the number of elements in B. And then I also told you the following. If the intersection is not empty, it means there is something in common, then things will change. Then the cardinality of A union B become the cardinality of A plus the cardinality of B. But when I take cardinality of A and cardinality of B and I add them, I will count the cardinality intersection twice. So I have to take it away. Okay, so this is the situation. This is called the addition principle. And this is, I usually call it the inclusive-exclusive principle. Too complicated for something not that hard, but very important principle. And the first one, when the intersection is empty, they call it the addition principle. So we mentioned both last time. Okay, now I am talking about this because you asked me about number 5D. So let me take number 5 and see what the scenario is in number 5 and then look at it. So number 5, here it is. This problem involves 8-digit binary string such that 100 and so on and so forth. So it means that the only thing we can put here is zeros and ones. And A is, so we have links 8. So we have the links in 8 of every term. And only zeros and 1 are allowed. So the first question is, of course, fairly easy. How many such strings are there? So what are, so quickly, how many such strings are there all together? I want a quick answer to part A so I can move on. Chat or talk, quickly.
2 to the 8th.
What? Repeat, I can't hear you.
2 to the 8th. So
2 to the 8th?
yes.
Absolutely correct. Each one of them, there are two choices. Two choices, and so on and so forth. B is how many ends in 0. So if we fix this one, so how many ends in 0? To the 7, because this is fixed. So I don't have really to worry about it anymore. How many have ones for their fourth, second, and fourth? So C is the following question. How many such strings have ones for their second and fourth digit? So for both of them. So to have ones for both, we always draw the picture. They have ones for their fourth, so this is constrained. They have one for their, second and fourth. So this is constrained, and the rest can move freely. 1, 2, 3, 4, 5, 6, 7, 8. So I don't have any choices here, I'm done. So I have choices for the rest, which give me 2 to the 6. Okay, so far so easy, no D. What is D? How many have ones for their second or fourth? How many have ones for their second or fourth? So which scenario are they really looking at? So they have here or here. So this is the string they are looking at. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So how can I deal with that problem? Okay. So how many have one here or one here? Any ideas? Okay, Nick tells me 2 to the 7 plus 2 to the 7. What's your thinking, Nick? Can you talk? Or you can't? Nick? Nick, can you talk? I can type. Okay. So, so Nick tells me 2 to the 7 plus 2 to the 7. Okay. Ooh, let's see. What is your thing? What is Nick thinking? I don't know. Anybody else? Where did he get the 2 to the 7 from? Anybody? Are you guys there? Okay, so in both cases, one position is fixed. In both cases, let us really split up what he means by cases. So I'm going to take A to be the following. I'm going to take, he tells me the cases. It means he said this is as a case. So I'm going to introduce the idea. Yeah, I'm going to introduce the idea of a set. So let A be all, what do they call them here? All the strings. So the collection of all strings that have one in the second spot. Okay, that's what he's saying, the first case. And B, all the string, so that's, I'm really breaking my problem because they have, that have one in the fourth spot. What do they want me to do? They want me to compute all the strings that are either in A or in B, either here or here. So I'm really looking for how many in their union, either here or here. So now, how many there are in their union? So it's how many in A plus how many in B if the intersection is empty. So now I go back. Can a string be here and here? Can a string satisfy both conditions? Yes or no? Please, I want answers. Can a string have a 1 in the second position and have a 1 in the fourth position? Absolutely yes. So the intersection of A and B here is not empty. So that's crucial. That's crucial here. So A intersect B is definitely not empty. They overlap. There are things here and things here at the same time. So to be able to do that, I have to take away what's in common. Otherwise, I will be counting it twice. That's really what you have to be careful with. So now, how many in A? That's easy. A is all the string that has 1 in the second spot. That's the 2 to the 7. Plus, B are those that have a string, they have a 1 in the fourth spot. That's 2 to the 7. But then, what's A intersect B? Are those, so A intersect B is going to be all the strings that have 1 in the second spot and in the fourth spot, which is also possible because it's in OR. That's in OR. So the last one are all those that have, so the intersection, let's write it in word. What's the intersection? That's all the strings that has one in second and fourth spot. Okay, so this is going to be now 2 to the 7 plus 2 to the 7 minus, if they have one in second and fourth spot, now how many of those there are? If they have one here and here, is 2 to the 6. And that should be the answer. So the original answer is not correct because this one is not correct because it did not take into consideration that those two sets are actually intersect. So I have to take away those that I'm counting more than once. Okay. So we have always to be careful. The minute it's either here or here, I have to ask myself, okay, am I repeating myself? Do the set meet? Okay. Is that clear? Now I look up at the second problem, which is 7b, and of course it's crucial. So 7b. 7. Actually, 7b is not really. I want to look at 3. Okay, I want to look at 3, and then probably I'll assign 7b again later. So I want to look at 3 for a reason in my mind, and the 7b, Chris, I will assign it later, and you think about it and answer you next time. Number 3. How many lists of length 3? So how many lists of length 3? And they are made out of the letter A up to F. Okay. Those are the letters. If, so length 3 up to F. If first, usually the first questions are easy. Repetition allowed. Repetition allowed. So 1, 2, 3. If I'm going to allow repetition, so 1, 2, 3, 4, 5, 6. I have 6 each. So it's going to give me 6 to the power 3. Okay, 6 and 6. Okay, B, it always follows. Repetition not allowed. One, 2, 3. So I have 6. If I cannot repeat, this has 5 and this has 4. So it's 6 times 5 times 4. So I'm not even asking you those questions because I think those should not be hard. Now C is repetition not allowed. So we cannot repeat and must contain letter A. Okay, we kind of did this before. So how many do we have? Oh, who can remember? So repetition, we cannot repeat, but we should have the letter A. What should be the answer to that one? Quickly, how did we do that? 20, because let's see, 20, I mean, I think I agree, I don't know. I don't know if I agree though. I don't know where the 20 comes from. Ah, okay. All right, we put 5 here. So there are, if I put A, since repetition is not allowed, 5, 4, that's 20. But A is fixed. A is fixed, I agree. But they did not tell you A is fixed in the first spot. Okay, they tell you it must contain A. Why you're fixing it in the first spot? That doesn't have to be. Okay, so it's absolutely 60. It could be here. or it could be here. So they really have, we have to take all possibilities. We cannot take one possibility. So it's going to be 3 times 20. And I want to make sure, can those who have A in this spot and those who have A in the second spot, can those intersect? It means, can I have repetition here and here? Because I'm adding. I said, how many here, how many here, and how many here? So the question is, you know, is there repetition? I mean, can I have a situation where I have A here and A here? No, because repetition not allowed. Otherwise, we have an issue. So the answer is 60. Okay. Now, E or D, whatever this is telling you repetition is allowed. Repetition is allowed. We're allowing repetition. And the list must contain A. Must contain A. How many cases are there? So how did you do this question? How shall I do that? Ideas? It's 3 times 36. Is it 3 times 36? I have to understand where the 36 is coming from. 3 times 36. No, I understand what he wants. Okay. So 3 times 36. Let's see if this is correct. So if I understand the logic of 3 times 36, which is Nick immediately pointed out to, is the following. I put A here, then 6, 6. Okay, that's the first scenario. If I put A here, 6, 6, 36. But here's the question. Are there things in common between this situation and this situation? I mean, can I have a string that satisfies this property? Yes. And satisfy this property? Absolutely yes, because they can repeat. So it's so the scenario AA is allowed here, like this scenario is allowed here. And the scenario is allowed here as well. So if I'm counting all those that have A in the first spot for sure, and A in the second spot for sure, and I take it's 36 plus 36, this is not gonna do the job because I will be counting a lot of the same scenarios. Okay, so thinking along the lines before is gonna not help us because I will have tons of repetition. Tons of repetition. So I cannot use that. So 3 times 36 will absolutely fail because you have to take away all the repetition, which is a nightmare in the making. That's why we're gonna try to find a way to go around it. Is that clear? All right, did you understand, Patrick? Does it make sense why I can't multiply? Patrick, with me? Okay. So now how are we gonna do that? How are we going? We're gonna do it actually in 2 different ways. How are we gonna take care of the situation? How we can break the problem so that I can do the counting correctly in this? So this is not working because of those repetitions. So how can we go around it? How can we break our problem? That's really the idea here, is break things into pieces we can control. So anybody have any idea? There are 2 approaches to this problem. I don't, it's gonna be a bit nightmarish. It's gonna be a little bit nightmarish. Try it. Yes, I can, but what's going to be nightmarish because I'm going to have first 3 scenarios because my A can be here. And it's not going to be easy to subtract all the intersections. We're going to go around that. We're going to make it in a neater way. Okay? Anybody can think of a way. Calculate by each 2 and calculate by each 2A and 1. Calculate by each 2A and 1 a scenario. Ah, okay, I like that. I think I understood what Patrick said. Patrick told me the following. We're gonna break the problem into pieces that are easy to control. So I'm gonna break them into the following pieces. First, I'm gonna take all the string that have, they must contain A, that have exactly, watch what I wrote, 1A. And then I'm gonna take all the string that have exactly 2 A's. Okay? Now, if I break it this way, will those 2 intersect? Because I put exactly 1, because they want me to contain A, exactly 1, those 2 will not intersect, because if it has exactly 1, it cannot have exactly 2. So I'm going to introduce 2 sets. You can call this the set E, which is all the string with exactly 1. And let me call this set F, which is all the string with exactly 2 A's. And what I'm really interested in, every string, if it contain A, is either has 1, or 2, or am I missing a case? Am I missing a case? Everything, if it contain A, either contain 1, it contain 2, or it's going to have exactly 3 A's. So I'm missing the scenarios of 3 A's. Sorry, E, F, G. So now what I'm really interested in is E union F union G. That's what I'm interested in. And all those do not intersect. So I can feel comfortable breaking them. So sometimes I have to be a little bit more creative. Very good. Now each one of them, I will do it separately. E, exactly 1A. Now I can go back to the scenario, exactly 1. How many of those? The A could be here, could be here, could be here. But I have exactly 1. So I don't have really repetition. So now I will have 6 choices, exactly 1, it means I will have 5 choices here, 5 choices here, because exactly 1A, 5, 5, 5, 5. So here I'm gonna have 3 times 5 squared. And now I am safe. I absolutely safe. I don't have repetition because I'm restricting my A's to 1. Here, how many situations I have? Okay, now I wanna take all the possibility of 2 A's. So my 2 A's could be here, here, and that could be free, non-A. My 2 A's could be here, here. This could be free, no A's. And I'm taking all the possibilities. And later on, probably next time, we start doing this without actually having to draw pictures. My A here, free possibilities. So those will give me that, how many of those I have? 3 cases, but now I only have 1 choice here, 1 choice here, 1 choice here by 5. Okay, so now what's going to be? Cardinality of E, 3 times 5 squared. And now I am safe, nothing intersect. F will be 3 times 5 plus string that have exactly 3 A's, there is 1 scenario. A plus 1. And of the problem. Okay, so that's one way to do it. And so all the idea of breaking things into easier pieces so we can control the scenario. All right, any question before I move on? Very good. Now, there's another way to do this problem. So that's one way that we should be fully aware of it. And then there is another way. But before I do this problem in another way, I want to really introduce the last principle, which is called the subtraction principle. And this principle is basically tells me that sometimes, okay, let me state it. And then I state it, I will go back to this problem and do it in a different way. Right. What does the subtraction principle tell me? It's again intuitive in terms of setting. Subtraction principle. Okay, then suppose A is a subset of a universal set U, where U is finite. So I have a universal set U, this is my U, and it's a finite, so I have finitely many elements. And I have a set A here, that's my set A. So there are a bunch of elements here, and of course, a bunch of elements right here, and there is a subset. So the subtraction principle tells me that the number of elements in U minus A, makes sense, is the number of elements in U, you take away the number of elements in A. It means the number of elements in the complement is the whole thing, take away how many in A. Okay, so this makes sense. It's very intuitive one, but it's very useful in the following sense that sometimes if I need to find the number of elements in a set, it probably will be easier for me to find the number of elements which are not in the set. And then I can compute the U minus A. So let me go back to the problem I take a minute ago, and let me redo it again. And I'm gonna use the subtraction principle. So let's go back to the same problem. So we're gonna go back to the same problem, which is number 3, part D. Okay, and what I was interested in is all the string that repeat. That's what I'm interested in. All the string that repeat, but and have at least one A and contain the letter A. Okay, all the strings that repeat and contain the letter A. So the way I'm going to think about it is the following. How can a string fail? How can a string be repeating but fail to be here? Fail to contain A. So what is the complement of this? What is the complement of that set? So I'm going to introduce my universe. My universe is all string that repeat. Okay. If I take the complement of this, it means how can a string fail to contain an A? How can a string fail to contain an A? It's easy, it doesn't contain an A. So the way I'm going to do it, instead of computing all those that contain A, I'm going to compute all those that don't contain A, and then I will take the cardinality of U minus the cardinality of those that don't contain A. So let me write this in a correct way. So I'm going to write the following: all string that repeat, all string that repeat and contain A. So this set is nothing more than all the string, you take away from it those that do not contain A. All string that repeat, of course, that do not contain Okay, so if I take every string, I take away from it that those don't contain A, but I'm left with that those that contain A. I stop for 1 second. So I'm really looking at the complement this time because the complement is easy to compute. So now the subtraction principle tells me to compute this, you take everything in U, the universe, and you take away this string, which are repeating, repeat, do not contain A. So you take this set from it. And now, is it easy to do that? So instead of looking at the set itself, I looked at the complement of it. I said, can I control the complement? And the addition, the subtraction principle tells me, yeah, if you can think this way. So this is going to be equal to what? What's the cardinality of U? U, all string that repeat. All strings that repeat. So since I have 3, 1, 2, 3, it's going to be 6, 6, 6, 6 to the power 3. Minus those that repeat but do not contain A. How many possibility I have? 5 to the power 3. And of the problem. Okay, so another way to do this. Now, if you compare what we got before, what you got here, we should have exact same number. So so if you add what we got before, I didn't do the math, and you add this one, we get exactly the same way. Okay, so it was two different ways to break up the problem into parts so we can work how it is. All right, so subtraction principle, actually, it's very useful. It's actually very useful. So I want those that contain A, and this was hard. I said, okay, let me look at those that don't contain A. Are those easy to compute? Yes, they are. So now I just have to take everything in the universe. I take away that those don't contain A. I end up with those that contain A. Okay, so two different ways of doing the same problem, and those are actually helpful for us. Right? Any questions before we go on? Yeah, always the U has to be clear. The universe has to be clear. You can't work without a clear universe because you don't know, you have to know what your universe is. Okay, any questions before we move on? So today we're going to learn, something that we've been doing, we did already, but it just have another fancy name to it. And we're gonna talk a little bit about permutation. Okay, so slowly. So permutation. What's a permutation? So suppose you have a set that have an element. A permutation of element of S is nothing more than a list. Is a list or ordered arrangement. Remember, when I say list, it means I'm thinking about order. That's what I'm thinking about. Order 1, 2, 3, which is different than 3, 2, 1. So that's what we mean by list. So it's a list or an ordered arrangement made of all the element of S. So if you have a set of an element, a permutation of the element is just a ordered arrangement made of all the element of it, where repetition is not allowed. Okay, so suppose S, this is a set, it consists of 3 elements, A, B, C. And the question is simple, list all the permutation of the element of S, all the permutation. Means basically I'm asking you to list all the ordered arrangement. So we just sit down and start doing them. So we've done A, B, C, that's what I mean. A, C, B. And now I can put B in front, A, C. Now I can keep B in front, C, A. So those are, then I can put C in front. That's what I mean, all the possible permutation. Then I can put C here, and then I flip those around, BA. So these are all the possible permutation. Okay, and how many permutation they have, it's not really hard. The number of permutation we know. since repetition is not allowed, we know that the numbers we're going to have is actually, how many? 3 times 2 times 1, which is 6. Okay. Now, example 2. Suppose S consists of 1, 2, 3, 4, 5, 6. 6 elements. So the cardinality of S is equal to 6. Another question is simple. What's the number of permutation of the element of S? So 1, 2, 3, 4, 5, 6. So what's the number of permutation? Quickly. 6 choices times 5 choices times 4 times, so as we said, it's really, we've done this, times 2 times 1. And as we know, a fancy way of writing this is the 6 factorial. So suppose S have A, B, C, D. If the cardinality of S is 6, then the number of permutation is actually 6 factorial. All right? So in general, what's the rule? What's the rule? The rule is, if you have any set, and if the cardinality of the set is n, so the set has n element, then the number of permutation, so the number of ways we can arrange the element of the set, the number of permutation is n minus 1, n minus 2 is going to be the n factorial. Okay. Let's take a very simple example to elaborate this before we move on. So let me, please, as I move the papers around, let me know if you're with me or not. So I'm going to put this simple problem on the board. So we have 25 balls numbered 1 to 25 are put in a basket and then drawn one by one. And the outcome is recorded as a list of 25 numbers as an ordered list. Anyway, the minute I say list, I mean order. So it means I take the first ball and I say which number it was. Let us say it's 12. And then I take the second ball. Okay, the number is, I don't know, 8. And I list those. So I have 25 of them. And the question is, how many possible is permutation, Chris? Okay, that's the topic. Got it? Okay. So now the question is, well, how many possible outcomes are there? So we draw, we can have 12, 8, or we can have, I don't know, 8, 13, and so on and so forth. Okay, so how many outcomes? Of course, we have 25, 24, we have 25 factorial. Because basically we have 25 numbers and we are putting them in a list. Now, second question. Of those outcomes, how many have all 13 numbers? First followed by 13 odd numbers. Sorry, it's not making sense to me. 13 odd numbers first, followed by 12 even. Okay, so of those outcomes, how many have all 13 odd numbers first, followed by 12 even numbers? So I let you guys, give you 2 minutes to do that. So we put them, we have tons of outcomes. Of all those, how many? The first 13 odd, and then so the first 13 odd and the 12 even. Okay, I give you a minute to think about it. Okay. Anybody else? I want comment on the answers. Please put on chat whatever answer you come up with. Whether you agree or disagree with Patrick. Agree? Anybody else? Anybody disagree? So how we're looking at this problem? Anybody disagree with Patrick? Please speak up. Okay, nobody agrees, so he may be right. 13 agree, so all right. So the first 13, first there are 13 factorial way to choose the first. And for each one way, there are 12 factorials. It's like the multiplication principle, 12 factorial to pick the second. So now I pick my 13. I have 13 factorial way to do it. And for each one of them, I have 12 factorial to pick my even. So by the multiplication principle here, multiplication principle, I have 13 factorial times the 12 factorial. Okay, so for each one of those, I pick 12. Okay, so this is so permutation of, of its a set is nothing more than taking the element of the set and putting them in order, and ask ourselves in how many ways can we do. Now there is something called a K permutation, which is the following. What's a K permutation? Okay. What's a K permutation? K permutation is actually what we've been doing, so but it has a name. So let S be a set, again, with an element, and K in integers, less than 1. By K permutation, it's an ordered list of K element of S, not of all the elements. So a regular permutation, it means you take all the N element and you make a permutation. K permutation, it means you take an ordered list of K element of S and you do a permutation of those. So that's what a K permutation. So for example, suppose S is A, B, C, D, E. Okay, here the cardinality of S is equal to 5. The question is, list some 3 permutation of element of S. So it means list some K, some ordered list of length 3 of distinct element of S. So, I don't know, I can pick A, B, C. That's a 3 permutation. Another permutation, I can pick A, D, E. So that's all possible permutation. And this is exactly what we've been doing so far. I can pick D, E, A, for example. That's another 3 permutation, and so on and so forth. Now the second question is, how many 3 permutations are there? Have we done this problem before? Have we done this problem before? So I have the set S, has 5 elements. And really my question, how many 3 permutation? It means how many ordered list of 3, of length 3 can I make using the element of A, B, C, D, E, and the element has to be distinct. It means the repetition is not allowed. So distinct element means that the repetition, that's crucial, is not allowed. That's what I mean by distinct element. It means we're not allowing any type of repetition. So how many 3 permutations of elements of S are there? S have 1, 2, 3, 4, 5. I have definitely 5 choices for this. Then for each one of them, I have 4 choices. That's the multiplication principle, and I have 3. So the number of 3 permutation is 5 times 4 times 3. Okay. Does this make sense? That's what we've been doing, nothing really new. Now I'm going to play like a very, very small game with that. 5 times 4 times 3. And I'm going to take it and I'm going to multiply it by 2 factorial and divide it by 2 factorial, like a small little game. Do I change anything in the expression? Basically, no. Multiply by 2, divide by 2, I'm not changing anything. But the benefit of this is that I can rewrite this in a more compact way if you want. So my numerator now will become 5 times 4 times 3. When I multiply it by 2 factorial, my numerator will become 5 factorial, and my denominator, which is 2 factorial, remain 2 factorial. So that's another way to write this expression. And this is, I do this because we're going to see a formula which is going to be based on this idea here. But so far, that's the permutation. I mean, if you don't even have to memorize anything. That's really the multiplication principle. So now I will introduce the first notation for permutation. So we will denote by P and K the number of K permutation in a set of n elements. So K represent the length of the list, and N represent how many elements we are basically rearranging. So P 5, 3 represent the number of 2 permutation. It means the number of 3 permutation. It means the number of ways, so I have a set of 5 elements, the number of ways we can make a list of 3 elements. And in my situation, P of 5, 3 was 5 times 4 times 3. Then I rewrote it 5 factorial over 2 factorial, but at least that I will explain again now, but it's just 5 times 4 times 3. So that's really what a 3 permutation is. So P 5, 3 represent in how many ways I have a set of 5 elements, in how many ways I can have a list, a ordered list of length 3 out of a set of 5 elements. Now we're going to find a formula for the general formula for P and K. Okay? But we're going to find it just based on our understanding. What's P and K? P and K is the following. I have a list, I have a set S. A set S whose cardinality is N. And I'm asking myself how many lists of K element, ordered of K element can I have? So 1, 2, 3, 4, dot, 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 and this is N. So we're going to assume here I have N dash. So how many? So P and K is equal to, I have N choices for this. I'm not changing my logic. Now if I have N, how many choices I have for this piece? Please write how many choices I have for my second choice, N minus 1. Okay, so I already, now, and then this one I have N minus 2, okay? Now, my list have how many elements? This N make no sense here. My list has, from here to here, I have K element. Okay, because the length is K. So this is N minus 1. This is going to be N minus 2. And I have to keep multiplying because I'm really doing it in the general case. So when I reach this one, the last one, okay, how many choices I have for this one? How many choices I have for this one? So here, I already took 1 away. Here, I took 2 away. So when I reach that stage, how many I took away already? I took all those away. So how many did I take away and how many is going to be left? So I have N, that's the total number of elements, but how many did I take away already? I took away k plus 1. Are you sure? Why k plus 1? If the whole thing is k, and I took up to here, means how many did I take? Take away. Do you agree with Nick? Why k plus 1? Did I take k plus 1 element? Or I took k minus 1 element? From here to here, I have k. And so that's the kth one. So how many? So the red up to here, it means k minus 1. So when I reach here, is everything, but I took away k minus 1. So what I'm left with is that much, which is equal to n minus k plus 1, if you want. Okay, I stop for a second. Did you understand why I took k minus 1, not k plus 1? Because I'm counting how many I already took away. So I have n, but how many I took away already? I took k minus 1 away. So for this one, I have total minus how many I took away. That's the choice I have. So I have to keep multiplying. So this is going to be n minus k plus 1. So far, nothing new. So far, everything we're doing is using the multiplication rule. Now we're going to do an algebraic manipulation to come up with the formula that we have to know the meaning of it and what it is. So this is equal to that. So far, I'm not going to change. Now we're going to do the following. Okay. I'm going to introduce factorial somehow. So what I'm going to do is I'm going to multiply this by n minus k factorial. And I'm going to divide by n minus k factorial. So I didn't do anything, but what's the purpose of that? So the purpose is the following. So this is going to be the denominator, n minus k factorial, and that's going to be n minus 1, n minus 2, etc. n minus k plus 1, n minus k factorial. Now, what's the benefit of doing all this mess, all this algebra? Look at the numerator. So the denominator is n minus k factorial. But look what the numerator become. Let us remember a little bit our factorial. Let's remember a little bit. If I take n times n minus 1 times n minus 2, so I will explain this, etc., n minus k plus 1 times n minus k factorial. This means what? This means n times n minus 1 times n minus 2, n minus k plus 1 times. What is n minus k factorial? It's n minus k, n minus k minus 1, etc. till 1 factorial. So if you combine this, n minus k plus 1, and then this should be before it, and before it, and before it. So my numerator is actually going to become n factorial. Okay, so that's really that's why we're doing this. So by doing this, my numerator here is actually n factorial. And this will give me the general formula for the number of ordered lists of links k out of a set of links n. So p and k, the number of permutation, is n factorial over n minus k factorial. And if k equal to n, what does it mean k equal to n? K equal to n, it means my list has the same number, the length of my list is the same as the number of elements of the set. So if k equal to n, it means basically I am ordering all the elements of the set. It means I'm doing the permutation of all the elements of the set. In this case, will be actually an n factorial, because if k equal n, it's n factorial over 0 factorial, but 0 factorial is 1, which is going to give me n factorial. So that's n factorial over z factorial 0, which is n factorial. And that will be the formula that we use for a permutation, which is equal to that, right? So let me make the problem a little bit more real so you understand what I am actually doing in here to come up with this formula. So I'll take numbers. So suppose I tell you, okay, how many P7, 4, for example. What's P7, 4? So let us understand it. It means how many, I have a set of links 7, and I want to make list of links 4. So the set have cardinality 7, sorry, and I want to make a list of links 4. How many of them there are? So the multiplication rule tells me it's 7 times 5 times 4. Where am I getting here those from? 7 times 6 times 5 times 4. That's the multiplication rule. Now the gimmick I did in this problem to come up with the formula is I multiplied by 3 factorial, what comes before 4, and I divided by 3 factorial. That's really the gimmick I did. And by doing this, my numerator became the 7 factorial, my denominator was the 3 factorial. The 7 is the number of elements in S, the 3 is the difference between the two elements. So that's really the gimmick we did here. So I multiplied by 3 factorial to make this into the 7 factorial. So that's how the formula is derived. Right, so let's make please ask questions if you don't understand anything or it's not clear. Right, let's make a very simple problem. So permutation is multiplication rule. The formula is just to make, it's what we've been doing. It's just like we can either repeat what we're doing or we can use this formula. It's really up to you. So let us do one small problem along those lines. So I'll put the problem for you in case you guys need to write it, and then we do it. It's 2 parts, A and B, fairly similar. So the problem is, in how many ways can a photographer at a wedding arrange 6 people in a row from a group of 10 people? So it's COVID-19 days, only 10 COVID-19, imagine wedding, and there are only 10 people in the party, but the photographer can only take picture of 6 people. And the order in which the people are put matters. So if we put John and then Mary, is different first, is different than putting Mary and John. And the question is, in how many ways can this be possible? Is this a permutation? What type of permutation is that? Can we think of this as a permutation? It's just, we have 10 people, distinct people, and the question is, you want to arrange them in group of 6. So how many list of 6 terms we have? All right? You can think of this as a permutation, 6 permutation. Or you can think of it multiplication rule. Okay, I have 10 choices, and I have 9 choices, 8, 7, 6, 5. So it's really the same ideas. So you can either do that, or you say that's really a permutation. So it's 10 factorial over the difference, 10 minus 6 factorial, which is 4 factorial. So you can do it either way. You can do it either way, okay? Over 4 factorial. So that's the formula. Please remember it very well. Now, part 2 is, in how many ways can this be done? If the bride and the groom are in the picture and they are next to each other. So I'm going to put an extra layer. I'll give you, of course, 2 minutes a little bit to think about it. As I said, not all. So that's the basic ideas. Every other problem should be obtained by, breaking the problem into simple scenario that we can really use what we know. Is this an answer, Peter? I have to know. Is this to answer my question? So it's 10 by 8 by 7 by 6 by 5. The problem, if you guys don't even explain, I am going to have a hard time, especially when you do the homework. If you give me an answer like this without explanation, I have to know where you're getting everything from, even if you're correct. Can you speak, Peter? Peter? Can you speak? Okay, so there are 5 places to put 2 people and 2 ways to arrange 2 people, and the rest are just the rest. Oh boy. All right, I'll give a minute for everybody else to interact with the problem, and then I will try to rip apart what Peter tried to tell me. Okay. Yeah, I'm reading this, but I want other students to pitch in as well. Tim, Simon, Rachel, Patrick, anybody? Nick, Logan, Gina, Emily, anybody else?
I'm in the car. I can't type.
Mm-hmm. Anybody else who's not in the car? I agree with Peter. Okay, let us figure out what I think Peter is telling us. So we have 6 spots. 1, 2, 3, 4, 5, 6. And we want those 2 to be in it. So basically, where can we put them? We can put them here. We can put them here. So these are the position where they can. We can put them here. We can put them here and here. So we don't really have any choices for them. So as again realize, we start breaking things. So we cannot always just have one formula. We have to break things. 2, 3, 4, 5, 6, and group. So these are the position where they could be. Now, but every position has 2 scenarios. It could be either the bride and the groom, but there is no reason where the bride can be first, or this. So every scenario we can either have bride, groom, groom, bride. And now what's left? Once I fix those, suppose I fix this scenario, I will have 8 for this guy. I will have 7 for those because 2 are being taken already. And I will have 6 and I will have 5 in my scenario. So what is the total? I will take this piece here. I will have 8 times 7 times 6 times 5. Okay, so once now how many positions for the bride and groom we have? We have 5 positions: bride, groom, bride, groom, bride, groom, bride, groom, bride, groom. So that's the position. And then for every fixed position, we can either put them bride, groom, or 2, which is going to give me the 2. This is bride, groom versus groom, bride. So we really have to sit down and start breaking problems to be able to do all of them. Okay, so I place them. After I place them, okay, these are every possible placement, nothing intersect. Those two cannot intersect because there is only one bride and one groom, so those cannot intersect. So everything are disjoint, and those are the position. I fix the position. There are that many possibilities for each one. But for every position, there are two scenarios, bride, groom, and groom, bride. And that's the end of that. Okay, so permutation is about ordered list, art of a set. Now this leads us to the other idea here, which we're gonna start talking about, is the idea of combination. So we started today, and next time we actually tear it apart. Any questions before we move on? Okay. So let's talk a little bit about combination. And as I said, next time we will do a lot of problems about it. But let's start to see what's going to be the difference between what we did and what we're going to do. So combination. So what we did is permutation. It means ordered list. Now we're going to start combination. Let's see the difference. So suppose I start with this example, fairly simple example. I take a set S, and my set, let us say, have A, B, C, D, 4 elements, nothing deeper than that. And I'm going to ask 2 questions. The first is what I did right now. How many ordered list, or how many lists, or I sometimes put order just to really remind you that I care about the order. How many ordered lists of length 4, of length 3, how many order of length 3 of distinct element of S can we make? So basically I'm asking about permutation of distinct element of S can we make? Okay. So ordered list of distinct elements. So that's really the permutation problem. So it means I have here 4 elements. How many permutation I can make? And okay, how many permutation I can make? We can make, so it's 3. They're going to be 4 factorial over 3 factorial. Okay, which is going to give me 4. And we can list them. I mean, we can actually list them. A, B, C.
Professor,
I'm doing something stupid, am I not? What?
wouldn't it be 1 factorial?
I know. Thank you very much. Okay. Because when I start listing them, I said, okay, this doesn't make any sense. So that's what I am really interested in, like A, B, C, A, C, B, etc., etc., etc. Okay. Now, second question is going to be different. Second question is, how many subset of 3 elements of element of S can I make? Is this a very different question? I'm asking a very different question. I'm asking here how many subset I can make of 3 elements out of S. The minute we say subset, really I don't care anymore about the order. You know, it's subset. So when I make subset, how many subset I can make? Okay, I can make of 3 elements only. A, B, C, that's a subset. ACB is the same subset, so I don't care about that. So then I can put ABD, that's a subset. And then I can put ABC, ABD, and then, okay, I'm done with that. So now I can take B, C, D, that's another one. And then I can make, what one will be left? And I can make ACD. Okay, Can you think of any other subset that I'm missing? Okay, so there are 4 of them. 4 subset. Okay, so 2 questions on the surface look the same, but they are very different. In the first case, I'm actually interested in all the ordered list of 3, so I care about this order. Here I'm just really asking you, okay, how many subsets? So ABC, that's one set. ABD, I don't care really about the order. So I definitely has way more less elements. Okay, now another way I can rephrase this problem, another way I can rephrase this is as follows. Instead of giving you this problem with subset, I can ask you the following. So I can rephrase, and I can say, for example, how many committees? So I have a class. So how many committees of 3 students can I make out of a class? Can I make out of a group? Can I make out of a group of, let us say, 4 students? Okay. So how many committees of 3 can I make out of a group of 4 students? Can I think of that as I thought about subset? Is this the same type of questions, but they've put it in a more interesting way? So here, basically, I can think of this as the following. My students are my set, so we can give them name. I can give them like Joe, Mary, what am I missing here? Peter, and let us say Hannah. Okay, so those are my students. And I need to pick 3 out of them. It means really basically picking subset of 3 elements out of a set of 4 elements. So here picking. So the question I ask, so this question is really equivalent to how many subset of 3 elements can I pick? The elements can I pick out of a set of 4. Okay. So asking how many committee of 3 students is really the same thing as how many subset of 3 elements can I pick. And in this case, I have 4 choices to pick my committee. Okay, so we're going to introduce the idea of a combination now, and I will be more elaborate with it next time. So what we're going to say is we're going to use a notation, which is the following. For 3, it means in how many ways I can pick 3 subset of 3 elements out of a set of 4 elements. So that's what this notation means. It's the number of ways I can pick. So you imagine a set have 4. How many ways can I pick a set of 3 elements out of it? Another way we can think of this is in how many ways I can choose 3 objects out of 4 distinct objects. And we're gonna give this a name, and this is gonna be called a N for choose 3, or we're gonna call it sometimes, this is called a 3 combination. 3 combination in a set of an element. 4 elements. So next time, that's the idea we will be really looking for, is how to pick 3. How many ways we can pick 3 out of 4, not in order, I don't care, but how many ways can we pick them? And you will definitely derive a formula for that, and we'll do tons of examples to elaborate this idea. Any questions before we move on? I'm working on your homework. I will hope to get it done by Friday. it will be up on Brightspace, and you guys will have, as usual, you will have a week to do it. So if I get it on Friday, you will have 1 week to do it after that. If I get it on Sunday, you will have a week. Whatever I get it out, you will have exactly a week to do it. In the meantime, I will always assign practice problem from the book that we're using, because this is helping us a lot to be able to grasp the material. Any questions from anybody? Anyone? Any question? Okay, so see you on whatever, on Monday. Bye bye, guys.